There we go. Okay, thank you. Thank you, Dawood. Yeah, all the people who cannot make it to the live session will thank you too, because otherwise those people would be totally lost. All right, so that's the first thing. So once again, if you do not get any confirmation that you have been added to the roster by next Monday, let me know and I will bring it up to the dean. You're welcome. And then for exam one, okay, so exam one, I want to schedule that to be let's see, 5 plus 7, so that's 12 days, away. So that would be the 27th, I think. Let's see, nope, 29th. Okay, so 29th.
You laughed at Axel, but
there we go. And I'm waiting for the website to
you
update.
laughed at Axel, but here you are.
Uh-oh, it's not updating. It was just updating fine, and then it won't update here. Okay, let me close the other one. All right, so exam one is going to be on the 29th of September. It's going to be a Tuesday. So basically, it's the Tuesday after next Tuesday, okay? And everything up to and including what we'll be talking about today will be in the scope of that exam. So everything up to and including binary number comparison will be in that exam. So everything from the very beginning of the class, when we talked about transistors, and then all the way up to and including comparison will be included in the exam. Now, some of you have taken classes from me already, and some of you have heard about heard from other people who have taken classes from me. So let me just kind of show. It is not updating. Okay, just give me a second here. And let me see if I can fix that problem.
I think it needs help.
Okay. So, okay, now it's fixed. Okay, so for the most part, it's going to be open books and notes and even Google. Okay, so if you want to use Google to find knowledge, it is okay with me. But it is not okay to be to collaborate with anyone, on the exam questions. So the bottom line is I'm testing the academic performance of each person. So whoever is turning in the answer, that answer should be of that person and only of that person. Okay. Books, notes, Google is okay because those are just resources to look up knowledge, and it's okay with me. Okay, when you go to work, you would hardly find an occupation where you cannot look up information. Now there are a few occupations where you do not want to rely on Google and Wikipedia, when you're doing your job. Being a surgeon is one of those. Okay, you don't open up a patient and then ask the nurse, iPad, and then look, and then use the iPad to look up something like which artery are we supposed to clip before we cut open this particular organ? Yeah, you don't want to do that, while you're in the operation, right? But other than that, okay, this is not, we are not being trained to become surgeons here, okay? Well, that's only because I myself cannot remember things very well. Okay, once I understand something, there's no way I would forget. Okay, because it's an understanding at that point. It is not just rote memory. On the other hand, if somebody is to ask me about something that is just a fact, but there's no quote unquote reason behind it, then I cannot remember it. So I don't really think it is necessary for us to remember all the facts. So what the test is about is about problem solving. Okay, so I assume that you guys have access to the knowledge. Okay, to the detail, right? To the very definitions. So the questions of the exam is all about solving problems. Okay, in the example of a car mechanic. Okay, I'm going to tow in a car that has problems, and then I just say, okay, here's the car. Get it fixed. I want to drive away with this car safely on the road in 80 minutes. Okay, that's kind of the nature of the test. Okay, but during those 80 minutes, if you need to look up information on the internet, if you that's fine. Okay, if you want to look up some books, that's fine too. But just not collaborate with somebody else. Okay, you cannot ask the next mechanic and go like, okay, can you take a look at my problem? That would not be okay. So that's pretty much the essence of what the exams are about. Okay, all right. So if there are no additional questions about the exam, because we will talk about that in a lot more detail on Tuesday. Okay, so next Tuesday I'll give you a practice exam, and the practice exam is the actual exam from last semester, or I should say the last time the class was offered, which is summer. Okay, so it's actually fairly recent. So we'll go through that particular exam one, and find out what kind of questions was asked, how they were asked, and so on and so forth. And I try my best to kind of find new ways to ask questions. Okay, so new problems to solve every semester. So you're more than welcome to dig up all the old exams. Okay, because I think it's helpful to kind of to look at all the past exams to understand how I asked the questions in the past. But there's no guarantee that it's going to be the same way for this semester, because I kind of like the process of doing something new. So that's kind of what is going to happen too, as far as the exams are concerned. All right. So now we're gonna get on to binary number comparisons, and those are basically flags. Okay, so we're going to define a whole bunch of flags in order to know what number, whether a number is less than another number or not. Okay, so that's going to be the focus for the rest of today and also today's lab. So we do have one lab today. It's due. Oh, okay. I haven't set up the due date yet. I haven't even opened it up yet, so I'm going to do that at the end of today's lecture. All right. So let's go ahead and click on binary number comparison. And if you have your browser open, go ahead and open the same document. So this way, when I have to flip-flop between the quote-unquote whiteboard and the module, you can just stay on the module, so you don't have to go back and forth all the time. All right, so we are starting with section 2. Okay, section 2 is stuff that should be really familiar to all of us already. What it is about is to say, you don't really need all the different comparison operators. If you're just given with less than, that should be enough. Okay, so let's check out this section and see why we only need less than. Okay, all right. So I just want to be redundant here. If you start with a less than, then obviously less than is going to be okay, not a problem. If you start with a greater than, you just have to reverse the left hand side and the right hand side, then everything is going to be okay, because now you have a less than again. So greater than can transform into a less than just like that. Okay, you just have to flip the two sides.
Wait, the creeper literally jumped off of a cliff.
All right.
And landed behind me and blew up.
Where is this material? It is in the modules. Okay, so if you scroll down, to on the modules, this is right here. So it's right below rotating 2020-09-15. So is that good, Daniel? You got it? Okay, all right. So getting back to here, so now we have one that is a little bit trickier. Okay, x is less than or equal to y. So if you're given with x is less than or equal to y, but you're only allowed to use less than, then we kind of have to use a logical operator. So we have an exclamation point here, which is logical not. So we have a logical not of x is less than, y is less than x, which makes sense, right? Because if x is less than or equal to y, then we know y is not less than x. So they really mean the same thing. So do we have any questions up to this point? All right, cool. So the other one, next one is x is greater than or equal to y, and just like in the second case, we just reverse the position of the x and the y, and we're good again. Okay, so this one is pretty easy. So now we are getting to not equal to. X does not equal to y. Remember, we are only given with less than. So the way to express x does not equal to y is x is less than y, or, so this plus here is really doing the same thing as a logical or, y is less than x. All right. Would these comparisons be presented in Logisim from form in the exam or like what we are showing now? Well, Logisim has certain things that can do comparison, but for the most part, we are not using those. Okay, so the way we look at comparison is quite different compared to what you see here using comparison operators. And then the last one is x equals to y. So x equals to y is basically, it is not the case that x is different from y. So we are basically looking at a negation of just the previous expression, so to negate that entire thing. In other words, if I say x equals to y, it is the same thing as saying it is not the case that x is less than y or y is less than x. So it sort of makes sense, even though it's kind of a long way to explain what is equality, but it works. So after this section, we now know that we only need the less than operator. All the other comparison operators like greater than, less than or equal to, greater than or equal to, not equal to, and equal to, those can all be done using just less than. Okay, when we are dealing with integers, obviously. Okay. Okay, there are no more questions, so we'll go ahead and move on to unsigned comparison. So this section 3, I know it is a little bit confusing. So instead of using this particular section here, we'll go ahead and use an example instead. Okay, so we'll use an example to illustrate how do we know a number is less than another number. In other words, from here on, our only concern is whether a number, a value, is less than another value. Okay, we are not concerned about greater than, we are not concerned about less than or equal to, greater than or equal to, not equal to, or equal to, because we know if we are only given with the ability to tell whether a value is less than another value, we can implement all of the other ones. So we are now only focusing on just less than. All right, so let's go ahead and get started with this section here. There's a whole bunch of math here. And all this math here is really just to show that we can rely on the borrow flag after a subtraction to tell us whether the minuend, which is x, is less than the subtrahend. Okay, so what we'll do is we're going to take a look at a few examples, if you will. Okay, and I think I learned how to do the block thing. So according to the documentation that I have found, I need to leave at least 4 spaces at the beginning before I actually type the content. So this should give us, you cannot see how I'm, okay, let me just kind of show you what I'm doing here. Okay, so we'll go ahead and compare, I don't know, let's try 0, 1, 0, 0, okay, and we'll compare that to 1, 0, 0, 1, okay. So just from looking at the number, we kind of know what the ordering is, right? But we still want to go through the comparison process. Okay, so we have a subtraction here, and then we want to know what is the result of the subtraction. So we'll go ahead and kind of do the template first, and then we go back in and do all the actual calculation. So this is also a nice way to review binary subtraction. So if you have any questions about binary subtraction, that would be a good time to ask. Okay, Duck asked, what are the flags? So a flag is basically something that can either be true or false. Okay, it's a Boolean value, but it is called a flag because it can direct the execution path when we get to the part where we start to introduce instructions. So they're called flags, because they're not just something that can either be true or false, but they can also be used, to direct the flow of execution, and that's why they're called flags. No, so plus, minus, exclamation point, equal, those are operators. So they are not. So I'll get to when we get to the flags. I'll show you what the flag is. Okay, we have encountered one flag already, which is the borrow bit after a subtraction. So the borrow bit, the overall borrow, is also known as a flag, the borrow flag, if you will, because that can be used, to indicate which way we should go, when we start to write programs. Now, we are not going to start to write any code until about week 8 or so. Okay, so we are about 2 or 3 weeks off from actually writing code. But when we get to the part where we start to write code, we need to make decisions, just like in a conditional statement in C and C++. And at that point, these flags will be very, very useful, because the flags are basically the only way that a computer at the lowest level can use to make decisions. So for the time being, okay, if you want to look at flags in a way that you're familiar with, okay, so you can basically look at these as Boolean, I'll call those Boolean values, okay, so each flag is a Boolean value.
The same biomes because you're all just running in circles.
Okay, so let me pause my mic first. All right, there we go. Hey, Lukey, I can pick you up from my mic. So yeah, if you can just speak a little bit softer. Okay. All right, so there we go. All right, so let's do this subtraction. Okay, so this really should not be a big surprise, because we already have seen subtraction already. Okay, so let me just label the rows. Okay, this is the row of Q, this is the row of T, this is the row of X, this is the row of Y, and the result is the row of D for difference. Okay, you can focus on the browser side. You don't have to look at how I type that in. Okay, I'm showing that how I type it in for those who are interested in Markdown, and also just so that you know that I'm working on something. Sometimes it may not be, it doesn't make sense on the browser side, but but you can get an idea of what I'm working on. All right, so for the Q row, okay, they're basically just the exclusive OR between the X and the Y bits. Okay, so I can work on this row in any order I want. 0, 1, exclusive OR has a result of 1, 1 and 0, also a 1, 0 and 0 has a 0, 0 and 1 has a 1. Okay, so I can work on all the bits on the Q row in any order I want, simply because each one only depend on the X and the Y bits of the same column. Now, when it comes to the T, unless we want to go through the math of the borrow look ahead equations, then we want to, because as much as we like the speed of borrow look ahead as a mechanism, it is not very easy for a person to do it, because there's a lot of it takes a lot of time to evaluate all of that. And the reason why that is the case is because when we perform those logical operations manually, we have to perform those operations sequentially also. In other words, I cannot perform multiple ANDs at exactly the same time, because when we think about these problems, the human mind is not built to perform those types of operations. So I really have to perform one AND, another AND, another AND. But the processor can just go like, okay, I'll do all 3 ANDs at the same time. Bam, done, right? So the advantage of borrow look ahead does not exist when we do things manually. But when you translate things into silicon and you want a computer to do it, then it makes all the difference. Okay? Just have one person per gate. Then we have a communication issue, because now we all have to communicate the answer to the person who's doing the OR, and that part has to be sequential too. So we have a lot of dependency on sequences when we are doing things. Just because we cannot operate exactly the same way as a computer. All right, so that's why we have to work on this column by column. So now we look at column 1. Okay, we have a 0 minus 1 from the previous column, so there's a borrow of 1. When we look at this column, we have a 0 minus 1 from the previous column, which has to do with the Q and the T, so there's a 1 over here. And when we get to here, there's a 0, right, because the XY is 1 minus 0, which does not have a borrow of 1, and then the QT are 1, 1, so there's not a borrow of 1 either, so that's a 0. And then the overall borrow, which is out here, the extra bit that is sticking out is a 1, because the most significant bit of x is a 0, the most significant bit of y is a 1, so 0 minus 1 does have a borrow of 1. Now we get to the last row, and once again this is just the exclusive OR between the Q and the T of the same column, so I can do this in any order that I wish. So this is 1 0 has an exclusive OR of 1. This one is 1 1, which has an exclusive OR of 0. This is 0 1, so it has a result of 1, and this is 1 0, which has a result of 1. All right, so now we have the binary subtraction done, and the first thing we want to do is to say, does it make sense? Okay, did TAC make a mistake? Which is fairly common. Okay, so we want to check. All right, so if you look at the value represented by this particular bit pattern, it doesn't matter whether it's signed or not, because the most significant bit is a 0, and as long as the most significant bit is a 0, it doesn't really matter either way, because the only difference between a signed versus an unsigned interpretation is when we look at the most significant bit, are we adding the exponent of 2 corresponding to that position, or are we subtracting an exponent of 2 corresponding to that position? That's the only difference. Now that's something that we talked about on Tuesday. Okay, so on Tuesday we talked about how to look at the signed value when it comes to the most significant bit. So in this case, this is really just 4. Okay, and in this one we do have to know whether we should look at it as signed versus unsigned, because we want to check whether the result makes sense or not. And when we need to do that, signed versus unsigned is significant. So in this case, we have 1 plus 8, okay? Because the most significant bit of 1, using the unsigned interpretation, is telling me the quantities of 8, not the quantities of -8. So we have 8 plus 1, which is 9. Okay, so this is 9. There we go. So now we look at the result. Now this is the funny part, okay? Because we want to look at everything as an unsigned value, so we look at the difference as an unsigned value as well. Okay, so this time we have 1 plus 2 plus 8, which is 11. So we have 11 over here, and now we go like, no, TAC, that makes no sense whatsoever. Okay, 4 minus 9 is at 11. I mean, come on, dude, that just does not make sense. Okay. Well, we are forgetting that we have an overall borrow of 1. Okay, the overall borrow of 1 is right here. Let me highlight that bit. This is the overall borrow of 1. So now the question is, oh, so that means even though TAC has $11 in his pocket, in his wallet, he is owing the bank a certain amount of money. So now the question is, what is TAC owing the bank? What is the amount the TAC is owing in this case? So now we have to look at this one and say, one of what, right? Well, that's not difficult to find, right? Because this is one, this is 1, this is 1, this is 2, this is 4, this is 8. So this one over here, let me just re-highlight the one that I'm talking about. So this one would be 1 of what? 1, 2, 4, 8, and the next one up is 16. Very good. So I'm owing the bank $16. Okay, so let me go back to the text window here. So I'm just going to add this part here with a borrow of 10000 in base 2, or 16 if you want to look at it as a base 10 number. In this case, yes, we are in debt. Okay, and that's because I only got $4 in my pocket to begin with, and somebody says, I need $9 from you, otherwise I'll break your fingers. Okay, and obviously I don't want my fingers to be broken, because then I cannot play the piano or type on the keyboard. Okay, so I go to the bank, I borrow $16. So when I borrow $16, I add the $16 that I borrow from the bank to the $4 that I already have. So now I got $20. And out of the $20 that I have, including the 16 that I borrow from the bank, okay, I take away, that person, the bully, takes away $9. Now, why the Boolean wants 9 instead of $10, that's beyond me, but that's, that's what the Boolean wants. So the Boolean got $9 out of 20, and that's why I got 11 left. So from that sense, it actually makes sense, right? 4 minus 9 is in fact 11 if we include the fact that I'm owing 16. The Boolean cannot possibly take all 20 because with only 4 bits, the highest value the Boolean can specify is 15. Oh yeah, this is cyberbullying. Oh, I like that. You guys are good. Yes, so it takes a minimum qualification to become a cyberbully. You have to understand Boolean numbers, Boolean stuff in base 2 first. That is a minimum. It's a min qual for being a cyberbully. In other words, we can ignore just about everything, from people who try to bully other people if they cannot show that they understand binary numbers. All right, but getting back, to the serious stuff. So is that okay? Does everybody understand, the math that is involved here? Why the result actually makes sense? 4 minus 9 is 11 with a borrow of basically 16. This borrow here is indicating that we are borrowing 16. So, but getting back to what we are really doing, okay? So what I'll do here is I'm going to go back to the point thing. The borrow flag, okay? Remember what a flag is? It's really just a Boolean value. Okay, let me represent this in a way, okay? I will put it in this way. I will put it in this way. So I will say the borrow B is the representation of the borrow, the overall borrow after subtraction. So I would say B is a 1 if and only if the minuend is less than the subtrahend.
Yeah, you can actually,
and this time I do have to use, make sure that this is using the unsigned interpretation, because the signed interpretation is different. If we were using the signed interpretation, we wouldn't have 9 for y. We would have something else, okay, which I'll talk about later. Alrighty, cool. So are we okay with this claim? Okay, this is just a claim, okay, and then we'll go back to the notes to find out, why is it the case. So basically, the borrow flag alone, the overall borrow after a subtraction alone, okay, without relying on anything else, can confirm whether the minuend, which we know as x, is less than the subtrahend, which is what we know as y, when we use this notation. All right, so it seems to make sense, right? Because if how much I have is less than how much is requested of me, then I have to borrow. Okay, it's basically as simple as that. Okay, so what we see in the module, okay, starting from here, all the way to pretty much the end of this thing here. Is to show why it works. Okay, this is basically just to show why it works. So everything all the way, including to up to here, is really a proof. Now so I'm gonna tell you right away that I'm not gonna ask you for a proof. Okay, but the mechanism of the proof is important nonetheless. Okay, because the mechanism of the proof is only making use of things that we have already discussed, which is how the borrow function, the B function works. So that part is still important, okay? But just because of the issue of time, I'm going to bypass everything. So we'll just go with the conclusion, which is stated here. The borrow flag is a 1 if and only if the minuend is less than the subtrahend when we decide to look at a bit pattern as the representation of something that is unsigned. Okay, so now we want to look at something that is signed. Okay, so section 4 is now saying, but what if we choose to look at a bit pattern and say that this particular bit pattern, which is all zeros and ones, is representing a signed value, which means it can be positive, but it can also be negative. Okay, so now let's go back and look at the same subtraction. So I'll go to the whiteboard here, and we're going to be looking at exactly the same subtraction here. So we go like, okay, using, so I will append, okay, this is what I'll do. Okay, this is the unsigned interpretation. So now we want to look at the signed interpretation. The signed interpretation of 0100, it's still 4 because the most significant bit is a 0. Remember, we add up all the other powers of 2 if it is not corresponding to the most significant bit. So if the most significant bit is a 0, then there's no difference between the signed versus the unsigned interpretation. But the other number, y, is not so fortunate, because it does have the most significant bit being a 1. So now we have a -8 added to a 1, which would give us a -7. So we have 4 minus -7. So when we have 4 minus -7, let's look at the result in this case. Okay, let's see what this is representing, because this is really, really wrong. Because as you can see, the difference also has the most significant bit being a 1, which means we have a -8. The other two bits would add up to a 3, so we have 3 minus 8, which is a -5. This is way wrong, isn't it? Because 4 minus -7 should not be negative to begin with, and somehow we end up with a -5. So this is already a problem, okay, because the result doesn't seem to make any sense. Now when we look at values from the signed perspective, the borrow flag has no meaning. Okay, so it doesn't give us a clue of what is going on. So you don't want to rely on the borrow flag at all when we are looking at values from a signed perspective. And then Daniel says, wait, so you take the values of the most significant digit and turn negative and others are added to it? Yes, that is what we talked about on Tuesday. Yeah, 2 days ago, we talked about this, and that is how we look at signed interpretation. I think it was toward the end of Tuesday's lecture. Okay, so you might want to review that part. All right, cool. All right, so I know that Daniel was present in the lecture, so that means maybe there's something about the way I explain it, or something about how it is not being integrated into things that we have already understood. So if there's if something looks confusing and you're not quite understanding why that is the case, after watching the lecture, just let me know, okay? Because it is possible that I forgot to include the actual logical link between two things that are related, and obviously without that link, things do not make sense. But at this point, I want to look at signed comparison, and in the notes, I have an equation or inequality, but I'm going to re-quote that inequality over here. So the inequality has to do with what happens, what about x is less than y, okay? So we say, okay, x is less than y, then what is so special about it, okay? So x is less than y if and only if, so I can subtract y from both sides, right? Okay, because that's just algebra. So we say, okay, if that is the case, then x minus y is less than y minus y. Does that make sense? Okay, if you just kind of look at the whiteboard side, x is less than y if and only if x minus y is less than y minus y. In other words, I'm just subtracting y from both sides. And this has nothing to do with whether y is positive or negative. It doesn't really matter because it's the same amount. In other words, if you look at a scale, okay, if it's tipping on one side already, then I can remove the same amount of material from both sides and the scale will still tip exactly the same way. It doesn't matter whether I'm removing something that is lead, which is heavy, or whether I'm removing something like helium, which is lighter than air, which gives us buoyancy. Because if I remove the same amount of helium on both sides, then the scale should still tip exactly the same way. Okay. All right. So I'm hoping this is making sense so far, right? So then I can now add to this and say, hey, but hold on a second here, because one side is there's no easy way to express it. Oops, x minus y, okay, but the other side, y minus y, hey, that's just 0, right? Does that make sense? I hope so.
Flashbacks to it.
All right, cool. All right, so now we say define d, which is our difference, to be x minus y. Okay, that's just definition. By definition, d is x minus y. So don't ask me why that is the case. I just choose to use a variable called d to become the difference of x and y. Okay, so now I can now say, okay, on the next line, I can now say x is less than y if and only if d is negative. I mean, based on the definition that we have mentioned in the previous line. Does that make sense? Because, we say x is less than y following a chain of reasoning if and only if x minus y is less than 0. But since I define d to be x minus y, so that means d is less than 0 if and only if x is less than y. Does that make sense so far? Okay, cool. And how do we know d is 0? I mean, d is less than 0. When we're looking at binary numbers, okay? Any signed binary value, okay, let me rephrase it. Any negative value represented as a signed bit pattern has the most significant bit being a 1. Yep, exactly. So Aiden has gotten it. Okay, the sign bit is really just a fancy word to say the most significant bit, or in a conventional way of writing numbers, it is also the leftmost bit. Okay, so all of those are referring to the same thing: sign bit, most significant bit, and leftmost bit. So they're all referring to the same thing. Okay, so here comes a question. Okay, how do we know that, if I add up all the other bits, okay, if I sum up all the powers of 2 corresponding to all of the other bits, how do we know that that sum cannot outweigh the negative value of the most significant bit? So let me show you what I mean by that. Okay, so we'll go ahead and look at 1111 as a base 2 number. Okay, so what value is it representing? Okay, the signed value is -8, because that's what the most significant bit is telling us, plus 4 plus 2 plus 1. So when you add up all of these things, we get -1. Okay, so that means, at least for this specific number, when you add up all the powers of 2 corresponding to the less significant digits, they cannot outweigh the negative value corresponding to the most significant digit, which is this one over here. And you can try this out with other numbers too, other binary numbers, and you will find that this is a universal truth as far as you can test. So now the question is, why is it this way? Okay, well, to prove that, okay, I'm not gonna do any proof because it's already in the module. So that proof is pretty much done up here. There we go. So the theorem is already here, okay? Because the theorem boils down to this, okay? Let me, okay, I can zoom in a little bit here. So the theorem is right here. This is the theorem that we want to prove. 2 to the power of n is guaranteed to be bigger than the summation of I going from 0 to n minus 1, and the term that we are summing up is 2 to the power of I. That is a theorem, okay? If you give me any value of n, that is at least 1, this theorem is true. So that is proven, using this particular proof down here, and is known as proof by induction. If you have not taken CISP310, you may not know what is proof by induction. Some of the math classes may use proof by induction as well, but proof by induction is usually not used in continuous math. It is usually used in discrete math. So maybe in linear algebra they would have proofs using proof by induction, but I think calculus may not use techniques like proof by induction that much, if any. They might, okay, because you can always expand a function as a series, okay, so they might get down to use proof by induction as well. But this class is not about proofs, so if you don't understand what is proof by induction and you have no idea what this is also talking about, it is still okay. Okay, it is not a big deal in this class, but it is a technique that you will learn in CISP310. All right. Okay, so what is the bottom line here? So the bottom line here is if d is less than 0, okay, d is less than 0, if and only if the most significant bit of the bit pattern of d is 1. Okay, that's the conclusion. Okay, if d being a value is less than 0, then when we look at the signed signed bit pattern representing d, then the most significant bit of that bit pattern is going to be a 1. Oh, okay. So if I chain all the reasoning already presented up to this point, that means x is less than y if and only if the MSB of x minus y is a 1. Because that's the chain of reasoning. We started off all the way here, then we conclude that x is less than y if and only if d is less than 0. But then we say, oh, but if d is less than 0, if d is an integer that is less than 0, then the signed bit pattern representing d is going to have the most significant bit being a 1. So if I chain this entire reasoning from the beginning all the way to this part here, so this is the conclusion. The conclusion is, hey, if we just look at the sign bit of x minus y in the subtraction, if that sign bit is a 1, then we can conclusively say that x is less than y. But we already saw one case where that doesn't work, because in this case 0, 1, 0, 0 is representing the value of 4, 1, 0, 0, 1 is representing the value of -7. So 4 is less than 7 is false, which means we are expecting the sign bit of the difference to be a 0, and yet we get a 1 over here. Oh, so that doesn't work. Okay, well, it doesn't work for a reason. So I want to show you another case where it does work. So let's go ahead and look at another case where it does work. I'm giving you another example here. All right, so we need at least 4 spaces, a whole bunch of 3 spaces here. We can compare 2 negative values. Okay, it will still work. 9 minus 4 is way too easy, Daniel. Oh well, 9 doesn't work. Okay, if you remember on the number wheel, okay, 9 does not work because we can only represent non-negative values. Given 4 bits, we can only represent non-negative values from 0 to 7. So 9 is not one of the values that we can represent when we choose to look at a bit pattern as a signed number. Okay, so good try there, Daniel, good try. So what we'll do is, if we want to stick with 4 bits, we kind of have to think about the range of values. So I'm going to use this one, 1110, okay, and the other number is, oops, okay, it doesn't like it that way. Okay, we need to have, there we go, 1111. Yeah, that will work. All right, so we look at this, And I'm just going to work out this entire row by itself. So we got 0 0 0 1 over here, and now I cannot do the same thing because when we look at the row of the borrows, we kind of have to work from the least significant bit to the most significant bit. So in this case, we have 0 minus 1 from the xy. Okay, so there's a borrow of 1, and when we look at this one, we have a 0 minus 1 here, so it has a okay, you guys cannot see where I'm looking at. So we have 0 minus 1, and therefore we have a borrow of 1 over here. And then we have 0 minus 1, which then has a borrow over here. It just appears. And because we have a 0 minus 1 here, then we end up with a borrow over here as well. And then we have an overall borrow of 1. And then we look at the actual result. So the actual result, which is the difference, is the exclusive OR of the previous two rows. Okay, so we have 0 1, which has a result of 1, and this is also 1, this is also 1, and this is also a 1. Okay, so this is just going through the very mechanical process. Okay, if you listen to me very carefully when I worked out all the bits, there was not even once that I mentioned subtraction. There's not even once that I mentioned because this is less than that, all I did was to refer to the borrow function that we talked about, which is not x. Okay, the borrow of x minus y is not x and y. Okay, that's a Boolean operation. And then to figure out q from xy is exclusive OR. To figure out d is q and t, but it's also exclusive OR. So all of those are bitwise operations. Okay, to get to the result here, I only rely on bitwise operations. Never once did I refer to the actual value and use arithmetic interpretation. Okay, so now we look at 1110 and we ask, on the number wheel for 4-bit numbers, what value is this representing? What do you guys think? How do we know what value is represented by 1110? First of all, is it negative or not? It is negative, and it's negative. Okay, so once we know it's negative, then the next question is, what is the magnitude of the negative value? Okay, this is one thing that we did last time, so I'm hoping that you guys still sort of remember that. So we start with 1110 as a base 2 number, equaling to the negation of the negation of the same thing. Okay, do you guys sort of remember this? Nope, it's not negative 7. So we take out one of the negation and then we substitute it with C2, which is 2's complement. So 2's complement is doing the same thing as arithmetic negation, and that's why we can take out one of the negation and replace it with a C2. So it's C2 of 1110 in base 2. And then 2's complement is bitwise not of the bit pattern, 1110 in base 2 plus 1. And then bitwise not is flipping all the bits. Basically we are just 1 becomes 0 and 0 becomes 1. So now we have 0 0 0 1 in base 2 plus 1. And when you look at 0 0 0 1, that's just 1, right? I mean, it doesn't really depend on the base in this special case. So we have 1 plus 1, which is 2. So now we have the negation, arithmetic negation of 2, which to us is really just negative 2. There you go. All right, so now we can go back to the table, okay, this little table over here, and we can now say, oh, okay, so 1110 is representing negative 2. All right, so, and then 1111 is representing negative 1. Now this time I'm not concerned about the actual difference. I'm concerned about the sign bit of the difference, which is just this. Oh, okay, I just selected one too many. There we go. Okay, so we're only concerned about this bit because this is the sign bit of the difference. So in this case, it works. Okay, the sign bit of the difference is a 1, which tells us that the minuend, which is 1110, is less than the subtrahend, which is 1111. And it does work. I mean, negative 2 really is less than negative 1. Okay, So sometimes it works and other times it does not. What is going on here? Okay, how come we cannot rely on just the sign bit to tell us whether the minuend is less than the subtrahend? So to answer that question, we go back to the previous one and then we look at this and go like, well, the first thing is we want to know whether the result, okay, of the subtraction is within the range that a 4-bit number can represent. So we look at 4, we subtract -7 from it. So what is 4 minus -7? I mean, you guys should be able to answer this question in a fraction of a second.
And potatoes and pizza. 'Cause you can
And yet we are waiting. Tick, tock, tick, tock. Come on, guys. What is 4 minus -7? 11. Yes, okay. But 11 is not one of the values that we can represent on the number wheel when we have 4 bits, okay? Because the largest value that we can represent, given only 4 bits, and we want to use the signed representation, is 7. The most negative value is -8, okay? So as a result, we just cannot represent the result of the subtraction. We have what we call an overflow situation in this case. Okay, so it is an error, okay, sort of, but it's called an overflow. Okay, so now we want to look at this and go like, okay, so when there's an overflow, then the sign bit cannot be relied on. So now the question is, but then how do we know there's an overflow? So you can look at this calculation here and go like, oh, okay, you know, we can see there's an overflow because 4 minus -7 is 11, and 11 is greater than 7, which is the highest value we can represent, and therefore we have an overflow. That works for humans, but it doesn't work for the computer because that conclusion is relying on comparing 11 to 7. But guess what? 11 cannot be represented using 4 bits. so the computer cannot use the same mechanism as we do in order to come to that conclusion. So Darwood is good, okay, is great, okay, that question is great because it is, it's basically, you know, the next thing we're going to talk about is how do we know there's an overflow, okay? All right, so I want you guys to kind of come up with your own conclusion of how we can end up with an overflow. So what I'll do is I'm going to give you another example that results in an overflow. So the first time we got an overflow is when we subtract a really kind of negative value from a positive value. That's how we ended up with an overflow. So this time we're going to subtract a positive number from a negative number and also result in an overflow, okay? Because I want you guys to kind of notice a pattern, okay? And here we go, okay? This is the example. So let's start with 1001, okay? And then we subtract 0101. Okay, that should work. All right, so we'll go through this subtraction first. And when we go through this subtraction, you know, I am going to use a very mechanical Boolean method to come up with the answer, just so that, you know, we know that we are not really cheating and utilize, you know, arithmetic concept in this calculation. So once again, we have the Q row, which is the exclusive OR of the X and the Y row. So we got 1 1 0 0 in this case, because, you know, it's really just the exclusive OR of the bits, you know, on top of it for each column. Now that we have to work out the borrow bits, we kind of have to do it from right to left, because, you know, the human mind cannot really utilize borrow look ahead, you know, the mechanism. So we are using borrow ripple in this case to kind of go, you know, one step at a time. So we have a 0 over here because 1 minus 1 does not have a borrow of 1, 0 minus 0 does not have a borrow of 1. And then we have 0 minus 0, 0 minus 0, which has no borrow into this place. And this time we do have a 0 minus 1, okay, between the X and the Y. So we do end up with a 1 over here. And then we have a 1 minus 0, which does not give us a borrow of 1. And then we have a 1 minus 1, which also does not give us a borrow of 1. So the overall borrow is a 0. But once again, because we are trying to look at things from the signed perspective, the borrow flag is totally useless in this operation. But I'm going to give it to you anyway, just so that we can have a complete calculation. So now we get to the difference row, which is just the exclusive OR between the Q and the T row. Okay. So now we have, let's see, a 0, a 1, and a 0, and a 0 over here. All right. So first thing is to look at the values that these things are representing and see whether they make sense or not. 1001 as a signed 4-bit number, is it representing something that's negative or non-negative? How do we know whether it is representing something that is negative or non-negative? We are only looking at 1001. It's not. Why would you think it's positive? MSB is not 0 because we are looking at 1001, the first one, the top row. This is what we are looking at. Okay, this bit pattern over here. Yep, that's right. Okay, so Daniel was just looking at the round number. It is negative indeed, but how negative is it? What is the value? So we use the same method that we used earlier, right? I mean, we take the 2's complement of this because that would give us the magnitude. And yes, so Daniel is correct. This is representing -7. All right, so we say this is -7. And what about the next row? What is 0101? It is non-negative, right? Because the most significant bit is a 0. We have a 1, we have a 4. Okay, you guys are all correct. It is a 5. So we have -7 minus 5, which should have been -12. But what are we getting down here? We're only getting a 4. Oh, okay, all right. So we have a overflow situation. Now, from our perspective as a human, we know there's an overflow situation because we say the actual value of -7, -7 minus 5 is -12, and -12 is more negative than -8, and therefore it cannot be represented, and now we have an overflow situation. That is a very human way of looking at this situation, which is great, okay, from our perspective. But it is not so great when you say, but I want to make a computer using transistors to do exactly the same thing, to come to the conclusion that we have an overflow. So using the semantics, is not such a great thing when you want the computer to do the same thing. So now we want to look at this and go like, so how do we know there is an overflow? Well, do you notice that when there's an overflow situation, the sign of the result doesn't make sense anymore? Okay, let me just go back to the previous example that we have already talked about. So this is the first one where the result does not make sense. We have a non-negative number minus a negative value, which should have ended up with a positive value, right? Non-negative value, but yet we end up with a negative value. So the sign of the result is wrong, okay? And then we look at the case that we just looked at here. We start off with -7. We subtract 5 from it. The result should be negative, and yet we end up with a non-negative value over here. So the sign is wrong again. So now we have a little clue of how to detect that after a subtraction, the sign of the result does not make sense, and that is overflow. Okay, so overflow is the same thing as saying the sign is wrong after a subtraction. All right, so now what we do is to look at all the cases of the sign of the minuend, the sign of the subtrahend, and the sign of the difference, and then we'll identify which one makes sense and which one does not make sense. Okay, so over here we're going to use a table this time. So the table, I need to find a way to describe all those things. I'll make it very clear then. Okay, so we have MSB of X we have MSB of y, and then we have MSB, oops, of d. So x is our minuend, y is our subtrahend, and then d is the difference. So we are only looking at the sign bits of x, y, and d in this case. And then what we do is make a table. I'm trying to remember how to make a table. Oh, I think I need a bar to separate the items. So we put a bar here, and then put a bar over here. Goggle. Yeah, we can goggle it. I think this is how we do it. All right, so the most significant bit of x is independent to the most significant bit of y. So one can be a 0, while the other one is a 0. One can be a 0, while the other one is a 1. One can be a 1, while the other one is a 0. And then one can be a 1, while the other one is a 1. Okay, so the table thing is not working. I know that I got this down the other day, and now I cannot remember. But that's okay because I got this whole thing bookmarked. So it's better than goggling because I can now actually just look it up in my bookmarks. All right, so I'm using a window that you guys cannot see. Under bookmarks, and of course when you need to find something you cannot find it. Okay. All right, fine. We'll do it the other way. Mark down tables. All right. So extended syntax markdown guide. Tables. Okay, we need to start with a bar first. That's how we do it. Okay. See, this is why my tests are all open book and open notes, because if I cannot do something, I cannot expect you guys to be able to do the same thing. Sort of. All right. And it doesn't seem to be working, so I must be missing something. And oh, okay, so the underlines also need that. So it needs, in other words, it needs to know how many columns there are. So we need okay, so do we need a beginning overbar, a beginning vertical bar? Yes, we do. All right, so that's a here, one over here. One over here and one over here. There we go. Cool. Okay. All right, so let me just make sure that the syntax is good for every single row first. All right. So now we have worked out all the possible cases for x and y. Okay, so the most significant bit of x can be a 0, and while it is 0, the most significant bit of y can be a 0 or 1. And when the most significant bit of x is a 1, then the most significant bit of y can also be a 0 or 1. But the most significant bit of the difference can be a 0 or 1 for the first row, can be a 0 or 1 for the second row, and so on. So we actually end up with 8 rows in this case. So let me just finish this part, and then we'll do some copying and pasting, because we need 8 rows like this. Okay, and that's because when we need to specify the most significant bit of the difference, it can also be a 0 or 1. Okay. Oops. There we go. 0 or 1. There we go. So now we have a table that is showing all the possible cases. You know, when the most significant bit of x is a 0, the most significant bit of y can be a 0 or 1, And when both of those are zeros, then the most significant bit of the difference can also be a 0 or 1. So we have 3 different bits, and therefore we end up with 8 different rows. Okay. But I also want one more column. Okay. So the last column that I need in this case is do we have an overflow? And it doesn't like it that because I haven't finished formatting the whole table. All right, so now that we have the table formatted, so let's see if it makes sense in this case. If I subtract a non-negative value from a non-negative value and end up with a non-negative value, do we have an overflow situation? Does the sign make sense in that case? Can it happen? Okay, come on, you guys can think about this. So I can say 3 minus 2, right? 3 is x, 2 is y, the difference is 1. So all of them have the most significant bit being a 0. Do we have an overflow situation in that case? 3 minus 2? So there's no overflow in this case. Okay, so we put a 0 because there's no overflow over here. So let's look at the second row here. Can that happen? Well, all we have to do is to reverse, right? 2 minus 3. So 2 minus 3 is negative 1, and negative 1 does have a most significant bit of a 1. But in that case, do we have an overflow? Okay, 2 minus 3 is negative 1, and as a result, the difference has a most significant bit of 1. But is it an overflow situation? Nope, it's not overflow. It can certainly happen. So we put a, okay, excuse me, put a 0 over here. So now we have x being non-negative, y being negative, and the result is non-negative. Do we have an overflow situation here? In other words, I can give you an example. Yep, okay, Daniel has got it. We do not have an overflow situation because I can give you an example. Okay, 1 minus negative 1. 1 minus negative 1 is 2, and 2 being a non-negative value has the most significant bit being a 0, and that makes perfect sense. We do not have an overflow over here, so we put a 0 over here. What about this one? We subtract a negative quantity from a non-negative quantity and end up with a negative quantity. Yep, okay, we do have an overflow here. What about this one over here? We start with a negative value, and so we have we subtract a non-negative value from a negative value and end up with a non-negative value. Do we have an overflow? We saw this case, by the way. Yep, we do have an overflow. So overflow is a 1. And what about this one? What about this row over here? We subtract a non-negative quantity from a negative quantity and end up with a negative quantity. Does the sign make sense in this case? The sign makes sense, right? If the sign makes sense, we do not have an overflow. All right. What about this one over here? We subtract a negative quantity from a negative quantity, and the result is non-negative. Can that happen? It can certainly happen, right? Because if I subtract negative 2 from negative 1, then the end result is 1, and we don't have an overflow here. Okay, so we don't have an overflow over here. And the last one is we subtract a negative quantity from a negative quantity and still end up with a negative quantity. I think we saw this a little bit earlier. We can subtract negative 1 from negative 2. The end result is negative 1, but it is still negative. So the sign of the difference is a 1. It makes perfect sense. Okay, so we don't have an overflow over here. All right. So we got a table. Okay, so we got this table over here. And we can see that only 2 rows out of the 8 have overflow being a 1. Okay, so now if I want to say, I want to define what is overflow, how can I define that? To do that, first, okay, I need to give the MSBs, specific names, because I don't want to have to type MSB of X, MSB of Y all the time. So we're gonna call this one,
No,
since it is the minuend, I'm just gonna call this M, okay?
minus 4,008.
Uh, here we go. This is the subtrahend, so it's the subtrahend. I should call it S, but since S is the sign bit, you know, so I probably want to use a different name for this.
My Y is minus 4,000.
Subtrahend.
Why would my Y be 4,000?
I don't want to use S because it's confusing, so that's why I'm thinking about it. And I'll call it N for now, okay? You know, just for this time. D is fine, so I'm just gonna call this D, like so. And then the overflow flag is just uppercase O. Uppercase O, like so. Okay. So now I want to define a function or an expression to do all this. Okay. So what is O equal to? Okay, how do I define O? Now, obviously, if you are to read the notes, the answer is all there already. But let's go ahead and derive this, okay? In other words, I want this to be a 1, but only when M is a 0, N is a 1, and D is also a 1, okay? Well, I just need a conjunction of not M, okay, oops, over here. So I just need a not M and N and D, okay? Okay, so let's look at this first, okay? So the negation only applies to M, so not false is true, so I take care of this. This becomes true after the negation. This is a true to begin with, this is a true to begin with. So when we look at this conjunction, it is going to be a 1, okay? It will generate this particular 1 when M is 0, N is 1, and D is also 1. So is that agreed that this will work for this particular row? Okay, very good. So now we say, but hold on a second here, Tak, you know, there's another row, which is this one here, that also needs a 1. Okay, fine, let's work this out, okay? So the way we work this out, okay, so we have some kind of an operator here in between, but we want to work out the other row. So the other row has M being a 1 to begin with, so we don't need to negate it, so we have just M in this case. But N is a 0, so if we want the conjunction to become a 1, we better negate N first. So we have a not N over here. And then over here, we also have D being false. And so in order for the conjunction to become true, we have to negate D as well. So we have not D. So now the question is, what do we use, you know, for this question mark operator here? Because we want both of these rows to be 1s, right? Yep. Okay, so Daniel has gotten it, and Darwood has gotten it, because, you know, we just need an OR in this case. Nope, I put the OR at the wrong place, and now I got rid of the N. I need it to be here. There we go. You can see me doing this, you know, because the distance between the monitor and me right now is kind of right between the focus range of my regular glasses, which I'm not wearing right now, and these are my computer use only glasses, which is supposed to focus at arm's length, and this is just a little bit beyond arm's length. So I cannot really read things that are small. As you already know, this is kind of small. Okay, I have a 4K monitor that is only 28 inches across. So this is actually really small on my screen. Okay, so indeed, this is how we define the overflow flag. The overflow flag is not M and N and D, the whole thing as a conjunction, or M and not N and not D, this whole thing as a conjunction. So should we use Boolean math on this? It is Boolean math. This is Boolean already. This plus is not an actual addition, it is an OR. And then the multiplication is not multiplication, it is, those are conjunctions. To optimize it. Well, this is pretty optimized already because we have two conjunctions that can occur at the same time, and when both conjunctions are done, we just have a disjunction to perform. So this is actually pretty quick. There's no need to quote unquote optimize it any further. All right, cool. All right, but we are not quite done yet, okay? Because our main objective is to find out whether x is less than y, okay? Just knowing the sign is sometimes wrong because we have an overflow, but sometimes it's right when there's no overflow. And the sign itself, normally, okay, can be used to indicate whether x is less than y, but not so when there's an overflow situation. So now we look at all of these things and go like, okay, how do we know whether x is really less than y? Now that we have all of these things going on around us, okay? So now let's take an inventory of what we have so far, okay? So the inventory goes like this, okay? We have the sign bit, we have the overflow bit, okay? And the sign flag is basically saying, the sign flag is a 1 if and only if x is less than y, but x minus y does not end up with an overflow. Okay, that's kind of how we have observed up to this point. Then what about the overflow flag? Okay, let's go back to this one over here. Whoops, there we go. Let's look at this one here. What if the sign flag is a 0? Well, the sign flag is a 0 can still indicate x is less than y, but only when there's an overflow. Okay, so the whole thing should read as the sign flag is a 0 if and only if x is less than y, but x minus y does end up with an overflow. In other words, the overflow flag is telling us whether the sign flag is lying or not. Okay, if you want to look at it that way. Okay, so the overflow flag is telling us whether the sign flag is lying or not. And the fact is, if the sign flag should be a 1, then x is less than y. Okay, so now we want to look at all the combinations and say, okay, in which cases is the result actually less than the other one? So we generate a table again. This time we have the sign flag as one, the overflow flag as another column, and then this time we have x is less than y as another column over here. And then we have this is needed in order to turn it into a table. And then we have all the zeros and ones, right? So we got 0, 0, and then put a question mark over here that will answer that question. And then we have 0, 1, and then a question mark over here. Then we have 1, 0, and a question mark. And then we have 1, 1, and also a question mark over here. So our job right now is to fill in all the question marks to say, okay, in this case, is it a 1 or is it a 0? So what do you think we should put over here? Yes, Aiden, S in this case is the most significant bit of D. That is correct. And I'll make it extra clear over here, okay? S is MSB of D. There we go. All right, so given how the bits are defined, what should I put in place of this question mark? In other words, the difference, the sign bit of the difference is a 0 and there's no overflow. You can't trust the sign flag in this case. So do we have a less than? can't it be both? Can't what be both? What is it referring to, Daniel? No, because we know that you cannot have x is less than y and y is less than x when x and y are integers. So we only want to know whether x is less than y. They may be equal to, but I'm only concerned about whether x is less than y or not. So in this case, because the sign bit is a 0, and the overflow says, yes, you can trust the sign flag. Remember, the sign flag is a 1 if and only if x is less than y. So in this case, because the sign flag is a 0, so that means we also know that x is less than y is true or false? False. Okay? Because generally speaking, if the sign flag is not lying, then the sign flag is a 1 if and only if x is less than y. So the only case where we cannot use that as an indicator is when there's an overflow. Because when there's an overflow, when O is a 1, then the sign flag is lying, which means it should have been the other way. Okay? Okay, all right. So let's work on this second row. In other words, we want to look at this question mark and say, well, is x really less than y in this case? The sign flag says, nah, not really, because the sign flag is a 0. Okay, remember the sign flag is a 1 if and only if x is less than y. So in this case, the sign flag is saying that, nah, I don't think so. I don't think x is less than y. But then the overflow flag is saying, ha, don't trust that sign flag, he's lying. Because when there's an overflow, the sign flag is the opposite of what it should be. So let's see, Kwan here is correct. It is indeed a 1. Okay, so the row taking question, I cannot remember what the answer was already, even though I just typed it right before class. So let's go take a look at the key, right? And it's over here. And it is compare, all lowercase compare, C-O-M-P-A-R-E. All right. So now that we got that out of the way, let's finish this table, because I really want to finish this table, because if I don't finish it and then we won't continue with this discussion next Tuesday, even though your lab does relate to this, but I want to finish it, okay, because this is really rather important. So in this case, yes, Daniel, it is compare. So there we go. The sign flag says, nope, x is not less than y, but then the overflow says, don't trust that sign flag, he's lying. So that means it is indeed less than. So we have a 1 here. Oh, okay, that's supposed to be a 0. This is a 1. Sorry, I put a 1 incorrectly onto the first row. Okay, let's move on to this one over here. Okay, this 0, this question mark. So in this case, the sign flag says, yes, x is indeed less than y. And then the overflow says there's no overflow. The sign flag can be trusted in this case. So that means it really is a less than in this case. And then on the last one, the sign flag says, yep, x is indeed less than y. The overflow flag says, no, don't trust that sign flag, he is lying this time. So that means it is actually not less than. So we put a 0 over here. So Tom is correct. So now that we look at this table, we go like, if I really want to know whether x really is less than y, I need to look at both the sign and the overflow flag at the same time. If I were to call x is less than y, its own flag, we'll call this the L flag, okay? Is there a quick and easy way to find out what the L flag is supposed to be? If I give you the sign flag and I give you the overflow flag, can you give me an operator that can generate the L flag from the S and the O flag? This is something that we have seen a few times already. Nope, it is not AND. The time when L is a 1 is when the sign flag and the overflow flag are different. It's not OR, it is exclusive OR. Very good. Okay, so Antoine and Dawood and Aaron are all correct. It is indeed exclusive OR. So now we can say L is defined to be sign exclusive OR with overflow. That is the definition of the L flag. So for the most part, the sign flag is kind of useful, but because it cannot be trusted all the time, we just go like, okay, you do exist, okay, occasionally you are useful, but most of the time for comparison purposes, I cannot just look at the sign flag. The overflow flag is really useful because the overflow flag can tell us when the sign flag is wrong. But by itself, the overflow flag is somewhat useless too, okay? So we cannot really just look at the sign flag nor just the overflow flag to know whether X is less than Y. And that's why I have this L flag defined here, because the L flag is a 1 if and only if X is less than Y in a signed comparison. And the L flag is always right because it is taking into consideration both the sign flag and the overflow flag. So this is really important. I really need to finish this because the lab tonight relies on this. So let me go back here and open tonight's lab. You need to know the key of tonight's lab anyway, and it has not been released. So let's go ahead and just open this up. And I'm keeping an eye on what Aiden is typing. All right, so the key or the passcode to the lab itself is flags. So you might want to write it down on a piece of paper. And I'll give you guys until Tuesday, class time to get it done. So that will be 5 days from today. Today is, so that will be the 22nd at 7 p.m. September 22nd, 7 p.m. Pin it. Can you guys pin? Or am I the only one who can pin? Oh, okay. Thank you, Tom. All right, so save and publish. There we go. Okay. I cannot remember whether I turn on that permission because I think all of these can be turned on or turned off. The administrator of the server or the guild has some control over that. All right, come on, Canvas, work. Okay, so looks like it is saved, and there we go. So you have your lab over this long weekend. But I would just try to get it done like right away. This is even though it is worth 12 points, it is not really particularly difficult, but it does refer to all the things that we have talked about today. Okay. Signed comparison versus unsigned comparison. I know we are running out of time, but I think this little last bit here is really important too. Remember what I said, when I pretend to be asking myself, so given this particular bit pattern, is it signed or unsigned? Remember that? And how I answer the question of what do you care, right? This is the answer to that question. This is the long version to that answer, okay? If you care because you're comparing, okay, then how do you know whether X is less than Y? If you're dealing with signed numbers, then you only look at the L flag, okay? You ignore the other flag. You ignore the borrow flag. The sign flag by itself is not too useful. The overflow flag by itself is not too useful. So you only look at the L flag if you want to look at X and Y as signed binary numbers. If you, on the other hand, if you say, no, we are only dealing with unsigned numbers here, and I want to know whether X is less than Y, then you only look at the borrow flag, okay? So which flag you choose to look at, okay, is how you choose to interpret the bit patterns. You look at the borrow flag when you're dealing with unsigned numbers. and then you look at the L flag when you're looking at signed numbers, when you're comparing signed numbers. Cool. And I'm just following up on some of the conversations over there. Oh, so Tom could not pin it. Okay, let me see if it's pinned. Nope, you're correct. It is not pinned. So let me try to pin that. There we go. Okay, so what Tom ended up doing was to quote it, but not to pin it. Okay, only I can pin. Okay, got it. So I got it pinned. Okay, so I'm just looking at the question here. So Tom is correct that L is S exclusive OR with O. And then Aiden is saying exclusive OR is also known as conditional negation. Okay, well, that's information, but we don't need to know that. Which flag or for signed numbers again? L is for signed number comparison. So that's for Tom. And then Aiden types here, okay. Okay, so I just pinned it. And what about unsigned? So unsigned numbers, you look at just the borrow flag. The overall borrow after a subtraction indicates whether the minuend is less than the subtrahend. Or to be more complete, the borrow flag is a 1 if and only if X, the minuend, is less than Y. All right. So all of that stuff is actually in the notes too. So reading the notes can be helpful. You can kind of skip the proof part, okay? But it is kind of important to understand which flag is for what, okay? And yeah, so that part is kind of important. All right. So are there any other questions for the live lecture part? I'm just staring at the text channel. So looks like we are good for now. All right. So the time is 35 right now. So I'm gonna go get a little snack to eat because I got an omelet already before the class, so I'm pretty good. So I'll be back in about 10 minutes. So for those of you who want to get the lab started like right away, go ahead and get started. After you get something to eat. And then I'll try to answer questions as you do the lab. I don't think this one is going to be too much of a problem because it's really just kind of the same thing as what we talked about today, and with the examples in today's lecture, I'm hoping the concepts are clear enough. But the lab has its own instructions too, so it's really just multiple exposure of the same thing. The notations can be a little bit different, so pay attention to the notations in the lab. Alrighty, cool. So I am going to stop the live stream and then I'll be back in about 10 minutes.